This is VLSI data conversion circuits, lecture 57. Over the course of several tens of lectures, we have covered the basic building blocks of a delta sigma modulator. I am taking a specific example here where I am assuming a CIFF type loop. There is an ADC there is a DAC, this is the digital data, this is U. Okay. So, we have discussed in detail what this is and how one goes about realizing the loop filter. We have gone and seen in detail how one can go and design a converter which has got very low latency, and the most commonly used version of the ADC architecture is the so called flash ADC architecture, where the time between the sampling instant and the time at which the data is available is as small as possible. Then the flash, as you know, gives out data or bits in thermometer form, and the DAC can also be realized as a thermometer DAC. We have seen all the advantages of a thermometer decoded version when we discussed DACs. So, we have seen this part of the puzzle too. One thing that we saw when we were discussing DACs is that no DAC will be perfectly linear, in the sense that the step size will not be the same for all codes. Okay. And the basic reason for this to happen is that whichever way you realize the DAC, whether it is a bunch of conductances coming together in parallel, or whether it is a bunch of current sources which are switched, there will always be device mismatch, and the moment these devices are mismatched, the levels will not be the same. Now, the details of whether you choose a binary weighted architecture or a thermometer decoded architecture are all just that, they are all details, but one thing that we must accept is whichever way we implement the DAC, we are most likely to get stuck with non-uniform step sizes, and at present the only way there seems to be of making the uniformity of the DAC steps better is to well, segmentation makes the DNL smaller, right, but if you have to improve the inherent matching, what should you do? And the bottom line is that you must choose passive elements or transistors which are fundamentally better matched, and that is only possible by making the devices or conductances larger and larger and larger, right. The same holds for capacitors too, though we have not taken a look at capacitor DACs, all right. Now, there is of course only a finite extent to which you can go on making the DAC elements larger and larger, right. So, if you want to improve matching beyond a certain point, it may, though it may be possible in principle, it is not practical, simply because the DAC will now have to become so huge that the commercial viability of the whole converter is called into question. So, today we will see how DAC mismatch affects a delta sigma loop and see what we can do about it in a way that does not increase the matching requirements of the DAC elements. In other words, we would like to get, in principle at least, the ideal SNR that you see in MATLAB, where you assume perfect matching, correct, but because the DAC elements are mismatched, the levels will not be uniformly spaced. We will quickly go over what happens to the performance of the modulator as such, given that the DAC levels are not uniformly spaced, then we will see why this happens, okay, and then we will figure out what all one can do in order to fix the problem. You understand? So, what we are going to be looking at in summary is to see what happens when there is mismatch in the DAC elements. Obviously, this is only relevant to a DAC with several levels. Okay, if you have only a single bit modulator, then a single bit modulator is inherently linear because there are only 2 levels, and through any 2 points you can draw straight lines. So, in principle there is no problem with mismatch at all when you have a single bit modulator. However, we have extensively seen all the advantages associated with multi-bit operation, namely what all advantages can you recall of using a multi-bit modulator over a single bit one? Yes, let us recall them quickly. Pardon? Okay, for the same NTF, what happens? What all happens? SQNR goes up, MSA also goes up, all right. Then what else? In a continuous time DSM, jitter noise, not jitter but jitter noise goes down. What else? Okay. Since the input into the loop filter is the modulator input minus the feedback DAC output, which is the input plus shaped quantization noise, correct. So, what is going into the loop filter is the difference between the two, which is largely shaped quantization noise. So, if the step size becomes smaller, the peak to peak amplitude of this shaped quantization noise also becomes smaller, thereby the loop filter is excited with signals which are smaller in amplitude, which means that nonlinearity is reduced, all right. What else can you say? For a single bit modulator, what will you choose the NTF to be? Pardon? How much? So, for a single bit modulator, typically you find that the modulator becomes unstable if the out of band gain is much larger than 1.5, okay. Whereas, for a multi-bit quantizer, you can use a more aggressive noise transfer function because the stability of the modulator is is a lot better, okay. So, in other words, you can also use multi-bit operation enables more aggressive NTFs. Does it make sense? Okay. Now, let us see how one realizes the quantizer. This is again just recap of the old stuff. The quantizer, as you all know, is an ADC and DAC in cascade, and device mismatches, whether they are in the ADC or in the DAC, will cause the behavior of the quantizer to become not what you anticipated it to be, correct. So, if there is device mismatch in the flash ADC, what happens to the behavior of the quantizer? Pardon? What happens to the quantizer as such? The quantizer is the ADC and DAC in cascade. What happens to the characteristic of the quantizer once there is mismatch in the ADC itself? Yeah, so the key point is to note that if the ADC has mismatch, in other words, the devices inside are not perfectly matched, then it is like moving the thresholds of the horizontal thresholds of the quantizer, okay, which can also be thought of as adding some error here, and fortunately this occurs in the same place as the quantization noise. So, the components of this error sequence which are in the signal band will get shaped out by the entire noise shaping process, okay. So, in other words, while mismatch affects both the ADC and the DAC, the effects of mismatch in the ADC are not within quotes visible to the outside world, simply because they are shaped out by the noise shaping process. So, we do not really need to worry about the mismatch in the ADC causing a change in the thresholds, it is all noise due to mismatch is noise shaped outside the signal band. All right. Now, let us see what happens when there is mismatch in the DAC. Now, the elements inside the DAC are not matched either, which means that what happens to the, how do you behaviorally model this as far as the quantizer is concerned? The horizontal thresholds remain the same because the ADC is fine. What changes is the output levels of the quantizer, okay. As shown in red in this picture, if there is mismatch here, it shows up as non-uniform thresholds in the DAC. Now, the question is, what happens to the performance of a modulator once the DAC has mismatch, and at a very vague level one can say, hey, if the errors are in the DAC levels, one can model this as some kind of noise waveform or error waveform being injected at the output of the DAC, right, but this is injected at the same place as the input, correct. So, the poor loop filter cannot distinguish between what is the input and what is the in-band component of this error waveform, right. So, the modulator at to a first degree will simply say, I am going to digitize as far as the modulator is concerned. You can think of it as rigidizing u plus E dac of t, right. So, the in band component of E dac of t will show up in the output spectrum. Is this clear? Now, let us see what exactly happens by taking an example, and before that I would like to remind you again that the flash ADC typically produces a thermometer code, all right, and it is quite convenient to use that thermometer code to drive the DAC directly if the DAC is also implemented as a thermometer decoded DAC, and most of the time the resolutions of the quantizers are modest, maybe 4 or 5 bits. So, implementing it as a full thermometer decoded DAC is not really a problem, all right, and this represents the thermometer to binary decoding, okay, and this can be done outside the loop. There is no need for doing this in the loop. Doing this in the loop is simply going to add to excess delay, because the DAC anyway takes a thermometer code. If you convert from thermometer to binary inside the loop, then you need to convert back from binary to thermometer again, which of course is, apart from being a waste of resources, is also bad in terms of delay. So, most of the time, I mean, so it makes sense to do this thermometer to binary decoding outside the loop, all right. Now, to take a simple example, I have assumed a 4 level modulator. So, how many comparators will be there? There will be 3 comparators, okay, and they will put out a thermometer code with 3 lines T1, T2 and T3, and these will get converted into a 2 bit binary code B1 and B0, all right. Now, the DAC of which I have shown an example here is simply 3 conductances of value 1 by 3 r in parallel, and the 3 thermometer decoded lines go and control these switches T1, T2 and T3. If T1 is high, the switch is closed, and what will happen to the current? What will this voltage be? Assuming the op amp is ideal, this is half Vref and this is Vref. So, this current will be, it will be 0.5 Vref by 3 R times T1, okay. If T1 is 0, the current is 0. The only reason I have chosen this strange half Vref and Vref is, so assuming that we are working with a single supply system where U is centered around half Vref and then rides over that half Vref. Is this clear? So, the levels of the DAC are 0 when all the 3 bits are 0, Vref by 6 R, okay, all right, 2 Vref by 6 R and 3 Vref by 6 R. Okay. So, if you have, I mean this is probably obvious, but if you have an n level DAC you need how many conductances? You need n minus 1 conductances. There is no holy reason to choose conductances, one could have had current sources instead, and in either case each of these elements are called unit elements, because they provide, each element provides one step of the feedback DAC waveform. All right. DACs like this, you could I guess also call them thermometer DACs. In the delta sigma literature, they are often called unit element DACs. Is this clear? Unfortunately, these three conductances are not exactly identical to 3R, there will be small random variations between the three. Okay. Now that we have got this out of the way, let us run an example where I have simulated a third order noise transfer function sampling at 3.072 megahertz, a 4 level quantizer, please note 4 level not 4 bit, okay. The O sampling ratio is about 32 and the noise transfer function is such that the zeros of the noise transfer function are not all sitting at z equal to 1, right. There are two of them are moved on the unit circle so as to minimize the in band noise, and from your assignment you must have seen that for a third order modulator, moving the zeros, making them complex conjugate improves the SNR over that where all the zeros are at z equal to 1 by 8 dB. All right. So, as you can see, there is the shaped quantization noise, this is the input tone sitting at 12 kilohertz. All right. This is the spectrum at the output of the modulator without any DAC mismatch. All right. The moment I put in DAC mismatch in the three elements, I have chosen quite randomly a 5% random mismatch in the elements, okay. And lo and behold, the in band spectrum which I was expecting or wanting to look like this now looks very different. All right. So, what all do you notice is the difference between what I want and what I have? So, two things are evident. One, noise floor increased, and two, harmonic distortion. Okay. Strangely, you see, or you might say strangely at first sight, you see all harmonics, not just second or third harmonics which are commonly used to seeing in when you do amplifier designs. Okay. You will find that other harmonics are way lower, okay. But here you see that not only do you see second, third, fourth, I mean a gamut of harmonics, right. So, the question is A, why is the noise floor rising? and B, why is there distortion, right. So, can we any intuition on why these observations make sense? Why do you think this makes sense? Well, I do not know why.
Gap mismatch effectively gives you errors which you can assume it to be added to input.
That is correct, but that does not say anything about spectral properties, is not it? So, why do you think this makes sense? What kind of nonlinear curve? And why do you, yeah, or rather, how did you conclude that you are multiplying the input, which input? Okay, with a? Okay, and how did you get this observation? No. Let us build on what he is saying. He observes that the distortion is happening because you are taking the DAX sequence and multiplying it by a, by multiplying it by a nonlinear curve, what he actually means is that he is taking the DAX sequence, which is a sequence of integers in this particular case going from 0 to, the DAX sequence is what? How many levels are there in the DAC? It is a 4 level DAC. So, the outputs are integers going from 0 to 3, ideally, that is without mismatch. With mismatch, it is, you can think of this as the ideal DAC, okay. And the real DAC is putting out sequence, you can think of the real DAC with mismatch as putting out a sequence where the step sizes are not linear or the step sizes are not equal. So, you can think of this as a mapping which takes 0, 1, 2, 3 and generates something which kind of straddles a straight line, okay. If there was no mismatch, the outputs of the real DAC should also have been 0, 1, 2 and 3, but what is actually happening is that the outputs are different. So, instead of staying on a straight line, the output voltages have veered off, and you can think of this as, in many ways. One way of thinking about it is, I take this sequence and pass this through some nonlinear curve, all right. Okay. And the only thing I need to worry about, since the input is a discrete bunch of points, is that all that I need to do is find some function which fits these 4 points. Okay. Clearly that will not be a straight line, because the points are veered off due to mismatch. Okay. So, in this particular case you can think of a third degree polynomial which will fit this input output data. Is that clear? Okay. So, this is some kind of nonlinearity. Clearly this so called nonlinear curve will have a large linear component, okay, and very small terms of the form x square, x cube and so on. Okay. But what happens when you take the input spectrum of the DAC is, say, something like this. Okay. This is the signal and this is the shaped quantization noise. What happens to the spectrum here after you take this sequence and pass it through a polynomial? What will happen? Okay, first we should expect, of course, harmonics, right. What else? What aliasing? I am taking a discrete time sequence and I am passing it through a nonlinearity. So,
the out of band noise, it can mix with the noise in some other component and.
okay. So, in other words, we seem to have had a handle on how to explain distortion. Now, it seems as if it does indeed make sense that there is distortion, because you have taken a sinusoid and passed this through a nonlinearity. Now, when you take this DAC input whose spectrum is not only signal, but also consists of shaped quantization noise, it has got frequency content all the way from 0 to pi, right. So, if you take 2 sinusoids at omega 1 and omega 2, right, and you add them up together, right, that is what this spectrum is telling you. It is telling you that there is some component at some frequency omega 1, there is some other component at frequency omega 2 and so on, right. When you take a sum of sinusoids and pass them through a nonlinearity, what happens? For example, if you take 2 sinusoids at omega 1 and omega 2 and pass them through a cubic nonlinearity, what all components can you expect? You can expect components at 2 omega 1 plus minus omega 2, 2 omega 2 plus minus omega 1, and of course 3 omega 1 and 3 omega 2. Okay. So, if there was a component here and a component here, when these two pass through a third order nonlinearity, what you will get is stuff here. 2 f1 minus f2 is equally spaced from f2, and so one will be 2 f2 minus f1 and the other one will be 2 f1 minus f2, all right. Similarly, if you have 2 closely spaced tones and you pass them through second order nonlinearity, what will happen? You will get f1 minus f2, and that is sitting in baseband, right, in the band of interest. Is this clear? So, this should explain or at least give you some intuition as to why one not only expects to see harmonics of the input tone, but also a rise in the in band noise. No. The okay, the input to the DAC is like this. So, I can find any number of tones which are close to each other, and these two will intermodulate through the second order stuff and fold back. These two will do the same thing, and so on and so on, right.
Even if they are apart, if the sum is more than pi, they will be equivalent to the having between 0 to this. Suppose the one is at pi by 2 and another is at say 3 pi by 4.
No, you will get the difference. If you have omega 1 and omega 2 and you pass them through a second order nonlinearity, you will get a component at omega 1 minus omega 2, alright. So, this is within quotes a very vague intuition as to why one must expect the in band noise floor to rise. You must understand that finally all these you must talk about in terms of autocorrelation function and pass spectral density, right, because we have assumed that quantization noise is white and uniform and all that, and the spectral density of the noise is this shaped thing, alright. And so, you had actually to calculate the in band noise, what one would have to do is to find the autocorrelation function of a sinusoid plus shaped noise upon passing through a polynomial type nonlinearity. Okay. This in general is a difficult problem to solve, right, and at any rate it is quite messy to solve, and at any rate we are not really interested in the exact value of how much in band noise is there and so on, right. We are more interested in eventually what to do to get rid of the problem. Okay. So, it is sufficient if you have intuition as to why this is happening. Is this clear? Okay.
Sir,
yes.
we assume that the noise due to DAC level mismatch is white.
No, why?
I mean, if we only have one DAC and the input is some binary code, which is equally spaced. So the mismatch of the DAC will be white, right?
No, why?
Because when you in the assignment that we did, we gave the DAC levels to be.
No. The mismatch in the DAC levels will be uncorrelated, right? But please note that spectrum is going through some nonlinearity. So, as you can see, the error is definitely not white. There are tones. Okay. So, all you can say is that this error waveform will have definitely components within the signal band. Okay. And you must also not forget that when you take a sinusoid plus noise and then pass them through a nonlinearity, the sinusoid is also interacting with the noise. So, I mean this is a grand mess. Okay. So, the only thing you can say for sure is that in band, okay, you will see both harmonics of the input tone as well as the noise floor rising, right. I mean, I guess one could also kind of hope against hope that somehow this error waveform, we know that it adds in series, I mean at the same place as the input, but if somehow by serendipity it turned out that the spectrum of this error waveform had no baseband components or no in band component, then we won't have to worry about mismatch at all. You understand? Is this clear? The problem is unfortunately that when you take the signal plus shaped quantization noise and pass it through a nonlinearity, you will get harmonics as well as an increased in band noise flow. Alright. So, now let us try and understand why this is happening. Okay. So, we have the intuition about why we should expect tones and raised noise floor. Let us look at it in a little more detail. Hopefully, this will give us some intuition as to what to do to fix the problem. Okay. Again, let me go back to the thermometer DAC example that I was showing you earlier. The DAC current I DAC is simply half Vref by 3R, that is Vref by 6R times T1 plus T2 plus T3, all right. Now, T1, T2 and T3, these are the thermometer code outputs, correct, and these are clearly functions of V, right. It is another matter that we decide to implement this thermometer to binary conversion outside, but if you had conceptually considered the ADC as producing a binary code V, all right, from which you internally produce the thermometer code, then you can say that these 3 drive signals for the 3 elements, unit elements of the thermometer DAC are functions of the output of the ADC. Is this clear? Yes, no? Okay. So, what functions are these? How are T1, T2 and T3 related to V? What all values can V take on? Zero, 1, 2 and 3, all right. And what values can T1 take on? Only T1, T2 and T3 can only take on values 0 or 1. Okay. So, let us start by drawing within quotes the transfer curve for T1 as a function of V, right. And what is the motivation for doing this? T1 clearly depends on V in some fashion. We are trying to figure out what that is. Pardon? So, for V other than 0, T1 will be 1. So, I will not be inaccurate if I say that T1 can be related to V by a transfer curve of this nature. What about T2?
You shifted by 1 to the right.
So, T2 is related to V in this fashion, T3 is related to V in, I can draw a similar picture for T3. Is this clear? All right. And why am I so curious to try and find T1, T2 and T3 as a function of V? The reason is that the IDAC can be thought of as coming from 3 components, right, T1, T2 and T3 each multiplied by Vref by 6R. Vref by 6R is a constant, so we do not have to worry about it. So, what you can think of this thermometer DAC as doing is it is taking the signal V, it is separating it into 3 paths, right, and converting each paths or converting it into 3 signals T1, T2 and T3 such that T1 plus T2 plus T3 is always equal to no, what is T1 plus T2 plus T3? T1 plus T2 plus T3 equal to V, correct, all right. So, you can think of the thermometer DAC as doing the following: it is taking the input sequence V, separating it up into 3 sequences, right, converting each one of these sequences into a current and adding the current sum. You understand? Now, how is it separating the input sequence V into these 3 sequences? I mean, or in other words, how are T1, T2 and T3 related to V? T1 plus T2 plus T3 equal to V, that is correct, right. And what I wish to point out is that T1, T2 and T3 are non-linearly related to V, correct. T1 plus T2 plus T3 is always equal to V, and T1 is some nonlinear function f1 of V, T2 is some nonlinear function f2 of V, and T3 is some nonlinear function f3 of V, all right. And the nonlinear functions are shown here. This is f1, this is f2, correct. Now, if you take a sequence V whose spectrum looks like this and passes the spectrum through a nonlinearity of this form, what can you expect in general? How will the output spectrum look like? In other words, how will the output spectrum of T1 look like? You will have harmonics, because this seems like a pretty stiff nonlinearity, correct. So, you can expect all kinds of harmonics, and what else? The in-band noise floor will also increase, because you have taken this sequence with this spectrum and passed it through a nonlinearity, right. So, just like we discussed earlier, you can expect that the PSD or the spectrum of f1 of V, which is the same as the spectrum of, what is f1 of V? What is f1 of V? T1, correct. So, the spectrum of T1 can be expected to be consisting of not only the input, right, but also its harmonics as well as some, the in-band noise is no longer small, because you have taken V which has got no in-band noise or very little of it at any rate, and pass this through a nonlinearity, and this nonlinearity will cause frequency components from everywhere to fall into the signal band. Is this clear? So, okay, right. Similarly, for both f2 and f3. In other words, the thermometer DAC is splitting up the input V into 3 components which are nonlinear functions of V. Okay. You can think of it as converting each of these 3 nonlinear sequences into waveforms and adding up the results, correct. Now, if there was perfect matching, even though f1, f2 and f3 are horribly nonlinear functions of V, when you add these three together, what spectrum must you expect? Pardon? T1 plus T2 plus T3 is V, correct, alright. So, even though the spectrum of f1 of V, f2 of V and f3 of V, which are the same as T1, T2 and T3 respectively, right, have a lot of distortion and an in-band noise floor which is very large. When you combine these three signals together, magically, or at least by construction, the distortion all goes away and the noise floor also goes down, and it will reach, I mean it will be the spectrum of V. You understand? Is this clear? So, this is what I show here, alright. So, these are, there are actually 3 spectra here, okay, corresponding to each of the thermometer code drive waveforms, and you can see clearly that each of them has got awful amounts of distortion and an in-band noise floor which is very large. However, this is the PSD of T1 plus T2 plus T3, and these waveforms are precisely such that when you combine them exactly with weights 1, 1 and 1, right, all these harmonics exactly cancel, and these noise components also add in such a way that the resulting noise is this. That is simply the shaped quantization noise which is characteristic of V in the first place. Does this make sense so far? Okay. Now, what do you think will happen if, so in other words, if T1 and T2 and T3 are precisely combined with weights 1, 1 and 1, you will get this spectrum. So, if the weights are off by small amounts, so instead of 1, 1 and 1, let us say this is 0.99, 1.01 and 0.98, what do you think will happen? The cancellation will not be perfect. So, you will see some residual harmonics and some residual noise floor, okay. And I mean, and if that happens to be much higher than the shaped quantization noise, then that is the one which will dominate. Does it make sense? Okay, we will continue in the next class.